Hello everyone, today we are going to discuss about directional stability, lateral stability and longitudinal stability. Let's start from basics. Aircraft stability. An aircraft is stable when if you disturb it, it returns to the balanced flight in its original altitude. This disturbance might be from wind gust, turbulence, control inputs, etc. An aircraft has three axes. You can see in this diagram longitudinal, lateral and normal. Longitudinal axis is indicated by a red color, lateral axis is indicated by a green color and the normal axis is indicated by blue color. Static stability. When an aircraft returns to its original altitude after a disturbance, it has a positive static stability. Think of a ball in a bowl. If you roll the ball up one edge of the bowl and let it go, it will eventually return to its middle of the bowl. Now imagine the bowl upside down with a ball sitting on a top. If you tapped the ball, it will roll off and increase it in speed as it did so, as the edges of the upside down bowl get steeper. This is called negative static stability. Now imagine a child seesaw or plank over a barrel that we tipped and it stayed exactly where we left in the tipped position. This is called neutral static stability. Dynamic stability. Dynamic stability is similar to the static stability except it has no reference to time and it occurs in a flight. If we take the first example of a ball in a bowl and imagine that an aircraft, we don't care how long it takes to return to the middle of the ball, as long as it does actually do so by itself. If it does so without going further out of stability, we call it positive dynamic stability. When stability is good, stability is not always wanted to desirable. For example, an aerobatics aircraft. The pilot who wants to perform a barrel roll does not want the aircraft fighting against him as they hold the position away from the original. However, the most recreational aircraft positive dynamic stability is desirable as we want them to be easy to fly and basically fly themselves if we release the controls. Longitudinal stability. Longitudinal stability refers to the ability of an object to maintain stability and control along its longitudinal or lengthwise axis. It is critical consideration in the design and operation of vehicles, aircrafts, ships, and other systems to ensure their safe and effective performance. Refers to an aircraft tendency to resist the change in its pitch, altitude, the angle between its body and the oncoming airflow. It essentially detects how well the plane stays balanced on the pitch axis, which runs from the nose to tail. Imagine a plane soaring through the sky. It gracefully maintains its level flight, adjusting to bumps and gusts without veering off course. This smooth controlled behavior is thanks to crucial aspect of the aircraft design called longitudinal stability. Good longitudinal stability makes flying predictable and comfortable. Pilots can maneuver the plane with minimum effects while passenger experiences a smooth ride. Conversely, an unstable aircraft would be constantly pitching up and down, making it difficult to control and unpleasant to fly. Key factors influencing longitudinal stability. Center of gravity. The center of gravity is the balance point of the aircraft. Its position relative to the aerodynamic center, where the lift forces act, plays a crucial role. A center of gravity further forward generally leads to more stability. Second, wings and tails. The size and shape of the wing and tail influences the pitching moment generated by the airflow. A larger tail relative to the wing creates a restoring force when the nose pitches up and promoting stability. Control surfaces. Elevators on the tail are used to control pitch. Their design and responsiveness contribute to the overall stability characteristics. Factors affecting longitudinal stability: horizontal stabilizer, center of gravity, center of pressure, propeller position, power setting, short fuselage decrease stability. Talking about maintaining stability, aircraft designers carefully balance various factors to achieve optimum longitudinal stability. This involves calculations, wind tunnel testings, flight simulations. Additionally, pilots utilize their skills and understanding of the aircraft stability characteristics to maintain smooth and control the flight. Let's see directional stability. Directional stability refers to the tendency of a moving object to maintain its heading when disturbed. Imagine a car driving straight down a road. If it encounters the bump or a gust of wind, the car might momentarily veer off course. However, the directionally stable car will naturally correct itself and return to its original path. Breakdown of key points. Axis of rotation. Directional stability concerns the stability of an object around an axis perpendicular to its direction of motion. For a car, this would be the vertical axis running through the center of mass. Second, disturbances. Various factors can disturb an object's directions, such as bumps, wind gusts, steering inputs, or even uneven surfaces. Restoring forces. A directionally stable object will have inherent features or a mechanisms that generates restoring forces when it derivates from its intended path. These factors act to bring the objects back to its original heading. The importance of the directional stability can be overstated. It contributes to the controllability, predictability, and safety of moving objects, from everyday vehicles to complex aircraft. By understanding the principles of the directional stability, engineers can design objects and are better equipped to handle disturbances, navigate their environmental effectively. Factors affecting directional stability: vertical stabilizer, center of gravity, propeller position puller is destabilizing, propeller position pusher which stabilizes it, wing diagonal which increases the stability, wing sweep back which increases the stability, short fuselage which decreases the directional stability. Let's look at some examples. First, cars. The position of the wheels, track width, wheelbase, and even aerodynamic all contribute to the car's directional stability. For instance, wider wheelbases generally provide a better stability. The diagram illustrates a four-wheel vehicle in which the front axis is located at a distance ahead of the center of gravity and a rear axle is distance b after the center of gravity. The body of the car is pointing in a direction theta while the traveling in a direction of psi. In general, these are not the same. The tire treads the region of contact point in a direction of a travel, but the hubs are aligned with the vehicle body, with the steering held central. The tires distort as they rotate to accommodate this misalignment and generate the side forces as the consequences. Second, airplanes. The vertical fin on an airplane plays a crucial role in its directional stability. When an airplane side slips, the fin creates a side force that pushes the nose back into the alignment with the airflow. Third is ships. The keel of the ship acts as a stabilizing fin, preventing it being easily swayed by the waves or wind. Let's see about lateral stability. Lateral stability refers to the ability of an object to maintain stability and control in side to side or lateral direction. It is a crucial aspect in the design and the operation of various systems to ensure their safe and effective performance. Lateral stability is particularly relevant in transportation modes like aircraft, automobiles, ships, and bicycles, as well as in structures such as buildings. Lateral stability, in simple terms, refers to the ability of something to resist the rolling or tilting sideways and maintaining its upright position. This concept applies to various fields, including aircraft. In aircraft, lateral stability ensures the wings stays level during the flight. This is crucial for safe and controlled maneuvering. When an aircraft slips means moves sideways relative to the airflow. The dihedral effect, the effect where the wings are slightly angled upward from the center, creates opposing forces on the wings, pushing them back to the level. This natural tendency to return the level flight is key to lateral stability. Factors affecting lateral stability: wing dihedral, which increases the lateral stability. Wing sweep back, which increases the lateral stability. High wing is more stable. Mid wing is neutral. Low wing less stable. Overall, the lateral stability is a crucial concept for ensuring the safe and proper functioning of many objects and systems in our world. It involves various mechanisms and plays a vital role in maintaining stability and preventing unwanted sideways. I hope this video is helpful for you. Thanks for watching.